After studying this module, you shall be able to learn what are cyclodextrins and when were they discovered. Understand the structural aspects of cyclodextrins, analyze their physicochemical properties and chemical properties, and learn about the formation of inclusion compounds by these cyclodextrins, and know about their applications in pharmaceutical and other areas. Now, what are cyclodextrins? Cyclodextrins are known as structurally related group of natural products which are formed during bacterial digestion of cellulose, hence the name cyclodextrin. Cyclodextrins are cyclic oligosaccharides which contain 1,4-alpha linkages in alpha-D-glucopyranose units and contain a sort of lipophilic central cavity and a hydrophilic surface. As you can see in figure is a bucket shape which has a thickness. The inner part of the bucket is lipophilic, whereas the outer part of the bucket is hydrophilic. Cyclodextrins were discovered by the French scientist named A. Villiers as the products obtained from degradation of starch, and named this dextrin as cellulosin because they were discovered from cellulose, degradation of cellulose. So, they were initially named as cellulosin in 1891. In 1903, another scientist, Franz Schrödinger, an Australian microbiologist who is the actual founder of cyclodextrin chemistry, identified two compounds of similar nature, which were crystalline and similar to cellulosin, that was obtained from bacterial digestion of potato starch, and he replaced the name of cellulosin by alpha dextrin and beta dextrin. These were later called as alpha cyclodextrin because of their cyclic structure, and beta cyclodextrin. After the discovery of gamma cyclodextrin, actually these alpha, beta and gamma cyclodextrin simply differ by the number of glucopyranose units in these cycles. Alpha has 5 glucopyranose units, beta has 6 glucopyranose units, and gamma has 7 cyclopyranose units. So, the discovery of gamma cyclodextrin in the year 1935, Freudenberg and Kramer has suggested the existence of larger cyclodextrins, that means larger than gamma cyclodextrins. Characterization and purification of delta, epsilon, tau, eta, theta cyclodextrins which contain 9, 10, 11, 12 and 13 glucopyranose units respectively. It has been accomplished recently. Cyclodextrins are important moieties which are useful as molecular chelating agents. They have a cage-like supramolecular structure that is similar to the structures formed by spherins, cryptans, cyclophanes, calixarenes and crown ethers. So, what is similar between these molecules is they have a cyclic structure which is a 3-dimension in shape, and they have a cavity inside them where we can encapsulate the smaller guest molecules. These compounds possessing supramolecular structures, why we call supramolecular structures here? Supramolecular structures are basically when the host molecule itself gets aggregated by the non-covalent interactions, and these aggregation gives you another moiety. So, we call it a supramolecular complex. In fact, the interaction of one guest molecule with one host molecule itself is a supramolecular assembly, because this is interacting, the guest and the host are interacting with non-covalent interactions. So, this itself is a kind of supramolecular inclusion complex. So, the compound possessing supramolecular structures often perform chemical reactions which involve intramolecular interactions. These chemical reactions do not result in the formation of covalent bonds between interacting molecules or like ions or radicals. Most of the interactions involved in this category are host-guest type, which we have done in the earlier module. They are called either dispersion forces or van der Waals interactions, or it can be dipolar interactions. Cyclodextrins are most important when compared with the supramolecular hosts which are aforementioned. The cyclodextrins have a huge range of applications in varied areas of drug delivery, pharmaceutical industry, and it is because of their characteristic ability of complexation and other versatile characteristic as well. The most commonly known pharmaceutical application of cyclodextrins is their ability to enhance the stability, solubility, bioavailability and the safety of drug molecules. So the main, as I mentioned in the earlier module, that the main applications of cyclodextrins in pharmaceutical industry is the safe drug delivery or targeted drug delivery. Now let us see about the structure of these molecules. As is indicated from the name, these are cyclic oligosaccharides, primarily consisting of 1,4-alpha D glucopyranose units containing a relatively lipophilic central cavity and an outer area which is hydrophobic in nature. The glucopyranose having the chair conformation, note all the glucopyranose units have chair conformation. So this chair conformation is the reason that cyclodextrins have a truncated cone shape like that of a bucket. So it has not a perfect cylindrical shape, but it is a cone-like shape, and this is because of the chair conformation of these glucopyranose units. The hydroxyl function groups are oriented to the exterior side of the cone, along with the primary hydroxyl moiety of the sugar residues at the narrow edge of the cone. The smaller one, you have the hydroxyl moieties, and the secondary hydroxyl moieties at the wider range, that means the upper part of the bucket. The central cavity is lined by the skeletal carbons, which is the chair conformation of the glucopyranose moiety. So that forms the central cavity of the bucket, and the ethereal oxygens of the glucose residues, which gives cyclodextrins a lipophilic character. The polarity of the cavity formed has been estimated to be close to that of an aqueous ethanolic solution. The naturally occurring alpha, beta and gamma cyclodextrins, particularly beta cyclodextrins, are of limited aqueous solubility. So beta cyclodextrin has the lowest solubility among its other members of the group. This indicates that complexes resulting from interactions of lipophiles with these cyclodextrins can be of limited solubility, which results in precipitation of solid cyclodextrin complexes from water and in other aqueous systems. However, interestingly, the aqueous solubility of the naturally occurring cyclodextrins is much lower than that of the analogous acyclic saccharides. So there is a strong intermolecular interaction bonding. There is a strong intermolecular hydrogen bonding, which is responsible for this property of the crystal state. Because of the hydrogen bonding, the solubility goes down, because intramolecularly when they are, associated with hydrogen bonding, they don't interact with the water molecules. So the solubility reduces. If you replace these hydroxyl moieties which are forming hydrogen bond with the molecule itself, then the solubility can be increased. So you can modify it by derivatizing. So pharmaceutically important cyclodextrin derivatives, which include hydroxypropyl derivatives of beta and gamma cyclodextrins and the randomly methylated beta cyclodextrin, or there are other derivatives such as sulfobutyl ether of beta cyclodextrin and the branched cyclodextrins such as glycosyl beta cyclodextrin. Now, a figure shows a substitution corresponding to the respective cyclodextrin derivatives, and all of these derivatives are pharmaceutically important derivatives. Now, let us see the physicochemical properties of cyclodextrins. The physical state of all three cyclodextrins is crystalline, and they exist as white powder. Cyclodextrins do not have a sharp melting point. However, they begin to decompose beyond temperature more than 200 degrees Celsius. Cyclodextrins have been classified mainly in two types, the naturally occurring ones and the chemically modified cyclodextrins. Biotechnologically formed cyclodextrins, that is alpha, beta and gamma cyclodextrins, differ in the number of glucose residues present in them. As I have mentioned, the gamma, beta and alpha have 8, 7 and 6 cycloglucopyranose ring respectively. The chemically modified cyclodextrin derivatives have been prepared with an aim to increase or modify the desired physicochemical properties, especially the solubility and inclusion capacity of the parent cyclodextrins. So by modifying the substituents on cyclodextrins, you can modify their host properties as well. You can increase or decrease the cavity size as per the guest molecule's requirement by just substituting or using different derivatives of cyclodextrins. The solubility of cyclodextrins depends greatly upon the temperature, as it is expressed by mathematical equations shown here, equations 1, 2 and 3 for alpha, beta and gamma cyclodextrins. You can easily see that concentration is a function of exponential of temperature, and these values indicates that the beta cyclodextrin is the least soluble among all the members. The table itself shows the physical data which shows the poor solubility of beta cyclodextrin. Cyclodextrins are largely water soluble except the beta cyclodextrins, which shows remarkably low solubility as compared to alpha or gamma cyclodextrins, which is evident from these values. At higher temperatures, the aqueous solubility of all cyclodextrin increases. You know that on increasing the temperature, solubility definitely increases. So this is true for cyclodextrins as well. When cyclodextrins are crystallized in aqueous medium, submolecules of water are included into the cyclodextrin cavity. So whenever you are having a white powder in your hand, that white powder is cyclodextrins which is having a water molecule in their cavity. Now other molecules of water are present as the integral parts of the crystal structure. The cyclodextrin inclusion complexes, whenever you form these inclusion complexes, they are produced by substitution of the included water molecule from cyclodextrin cavity by appropriate guest molecules. That means the guest molecule removes the water molecules from the cavity because it forms a more stable inclusion complexes. Cyclodextrins show insolubility in almost all organic solvents, but show solubility in some polar aprotic solvents. Solubility depending on temperature of cyclodextrins may alter when it complexes with the guest molecules. So that means solubility depends on the chemical interaction of the guest and the host. The inclusion complex shows greater solubility than the cyclodextrin itself. If the guest molecule has relatively higher solubility in water, then the solubility of the entire inclusion complex will increase. In contrast, the inclusion complex formed with the guest molecule showing poor water solubility generally results in a lowering of solubility of the cyclodextrin itself. Although the solubility of inclusion complex is generally less than that of the cyclodextrin itself, it is greater than that of the guest molecule definitely. Let us see more of chemical properties now of these molecules. Cyclodextrins do not have any N groups which are reducing in nature. So when we oxidize these molecules with periodate, all the alpha, beta and gamma cyclodextrins will split open the glucopyranose ring. However, formic acid and formaldehyde are not formed as the byproducts. This proves that cyclodextrins do not contain any free end groups. The glycosidic bonds of cyclodextrins are fairly stable towards the basic conditions and even at elevated temperatures. Cyclodextrins show a better resistance to acid hydrolysis as compared to starch. Strong acids like hydrochloric acid tend to hydrolyze the cyclodextrins, thus yielding a mixture of oligosaccharides ranging from open ring and simpler products such as glucose. So whenever you are adding acids to these cyclodextrins, you are not getting the cyclic structure is not retained. You get open chain structures or sometimes a single unit like glucose itself. The acid hydrolysis rate tends to increase as a function of both increased temperature and the acid concentration. So you can see the more concentrated the acid is, the simpler products will be more. That means it is going to break the glycosidic linkages of cyclodextrins. The cyclodextrins hydrolyze minimally in the presence of weak acids like organic acids such as acetic acid. Cyclodextrins show resistance to acid catalyzed hydrolysis compared to linear sugars, and the ring opening rate of cyclodextrins increases with increasing cavity size. That means the most stable of all cyclodextrins will be alpha cyclodextrins, which has only 6 units of glucopyranose. So alpha, beta and gamma will be the most unstable one, because as you increase the cavity, the ring opening rate by using acids, that also increases. Now, how the inclusion complexes are formed by these molecules. The most intriguing property of cyclodextrins is these molecules are able to form solid inclusion complexes, also known as host-guest complexes, with a very large range of solid, liquid and gaseous compounds by following a molecular complexation protocol. Dimension fit between let us say in such complexes, a guest molecules is held within the cavity of the cyclodextrin host molecules, as you can see in the figure. In fact, you can easily see a small molecule going into the cavity of these bucket shaped molecules and forming these inclusion complexes, and these guest molecules are held within these buckets only by these non-covalent interactions. The guest goes inside only if it has the size absolutely equivalent to the cavity. Okay. No covalent bonds are cleaved or formed during this process, from which the inclusion complexes are obtained. The main driving force behind complex formation is the expulsion of the enthalpy rich water molecules from the cavity of cyclodextrins. As I have mentioned, whenever the guest molecule is coming inside the cavity, the water molecules which were already sitting into the cavity will move out, and this is enthalpically favorable. That is why the inclusion complex formed will be more stable. This helps the system to attain a apolar association and decrease of cyclodextrin ring strain, resulting in a more stable lower energy state. The binding of guest molecules within the host cyclodextrin is not a permanent phenomena. So it is a reversible process. The guest can come in and it can move out depending on the stability of these host guest complexes. It is rather a part of a dynamic equilibrium. So the guest molecule and the host molecule, the inclusion complex is formed as a dynamic equilibrium between these molecules, wherein the guest can come in and at some part of time it is going out. So you have an equilibrium where you have some concentration of the inclusion complex and some concentration of the individual host and guest molecules. When an inclusion complex of a given cyclodextrin with a guest molecule is formed, it is a function of two key factors. Now, what are these key factors? The first one and the most critical factor is the steric factor, and it depends on the relative size of cyclodextrin. As I told you, the size of the guest and the cavity of the cyclodextrin must match to form the inclusion complexes. The size of the guest molecule or the certain key functional groups within the guest. Wrongly sized guest molecules will not fit appropriately into the cyclodextrin cavity. The second factor, which is the thermodynamic factor. Here, thermodynamic interactions form the important factor between the different components of the system. That means the guest and the host molecule, which is cyclodextrin in this case, as well as the solvent molecule. So in order for the complex formation to take place, there must be a favorable net energetic deriving force that pulls the guest into the cyclodextrin. That means when the guest comes inside and the water molecules move out and the solvent is also disturbed. So the whole process should be enthalpically favored, or I would say it should be thermodynamically favored. While the height of cyclodextrin cavity is alike for all three types, whether it is alpha, beta or gamma, the height of the cavity is same. The number of glucose units determine the internal diameter of the cavity and its volume. So the smaller alpha cyclodextrin will be encapsulating smaller guest, and gamma cyclodextrin will be encapsulating relatively bigger guest. Based on these dimensions, alpha cyclodextrins can typically form complexes with low molecular weight molecules or compounds like with aliphatic side chains. Beta cyclodextrins, which are relatively bigger, can complex with aromatics and heterocycles, and the gamma cyclodextrin, which are the biggest out of three, can accommodate larger molecules such as macrocycles or sometimes steroids. Now let us have a peek into the applications. Although the applications are enormous, but we can definitely take a few examples to stress upon. As each guest molecule gets surrounded by cyclodextrin individually, the molecule is microencapsulated from a microscopic perspective. Now when this guest molecule gets encapsulated in the cavity, this gives rise to fruitful changes in the chemical as well as physical properties of the guest molecules. Let us see how the changes occur when a guest molecule gets encapsulated in the host molecule. The changes can be the light or the oxygen sensitive substance can get stabilized. if we have a guest molecule which is light sensitive, encapsulated into the host molecule, it is not directly interacting with the light, so it gets stabilized within that cavity. Another property changes are like guest molecules, and the chemical reactivity of both the guest as well as the host molecule gets modified. Of course, because there is a thermodynamic stability that we have achieved, so chemical reactivity will definitely be modified in this case. Now, example, volatile substances, they get fixed as a place, so they are not evaporating. Once they are encapsulated, their volatility is completely vanished, so they get stabilized and fixed at one place. Another one is solubility of many substances is greatly improved. So if you have more soluble molecule, it will improve the solubility of the inclusion complex and vice versa. Liquid substances often get modified into powders now because we are increasing the molecular weight. When a simple guest molecule has a low molecular weight and the host molecule has a comparatively higher molecular weight, but the inclusion complexes have even more higher molecular weight. So it may change the state of the guest molecule from liquid to solid or the powder form. So this kind of interaction also aid for protection against degradation, which is caused by microorganisms. So it's a kind of protection that we are giving to the guest molecules. We have a host molecule which are encapsulating, or I could say protecting these smaller molecules within their cavity. So it protects against the degradation by microorganisms, and then they also lock in the smell of these guest molecules. So bad smell or taste often gets completely masked in these inclusion complexes. The color of substances like pigments, they can also be masked when they are under this interaction of guest and host molecules. The catalytic activity of cyclodextrins with guest molecules also get modified. You know that cyclodextrins also act as a good catalyst in various reactions, so their catalytic activities also is modified depending on the guest molecules encapsulated within their cavity. These characteristic properties of cyclodextrins or their derivatives make them appropriate for applications in analytical chemistry, pharmaceutical industry, agriculture, and in the development of food flavors, or let us say toilet articles. So there are enormous applications of these molecules. One has to just be more creative to identify more applications of such molecules. Now, recent advancements in biotechnology have resulted in unprecedented improvements in the efficient manufacture of cyclodextrins, minimizing the cost of these materials and making them much more purified cyclodextrins and their derivatives, and they are easily available, economically cheaper. In conclusion, it is a unique architecture and the chelating property of cyclodextrins which are becoming an important part of the biotechnologist options in the horizons of biocatalysis, encapsulation, and the controlled release in many pharmaceutical applications. So you know that how beautiful these molecules are and how much, I would say, the modification possibility are there, and now because they are economically cheaper molecules can be synthesized with at a lower cost, they can be easily modified to get the required properties, and the uses can be enormous. So let us summarize what we have learned about these cyclodextrins. The cyclodextrins were first discovered by French scientist whose name was A. Villiers, and are known as structurally related group of naturally occurring products formed during bacterial digestion of cellulose. The glucopyranose units having their chair conformation is the reason of cyclodextrin having a truncated cone shape rather than a perfect cylindrical shape. The physical state of all three cyclodextrins is crystalline, and they exist as white powder. Cyclodextrins do not have a sharp melting point, so they decompose at temperatures above 200 degrees Celsius. Pharmaceutically important cyclodextrin derivatives are hydropropoxyl derivatives of beta and gamma cyclodextrins, the randomly methylated beta cyclodextrins, sulfobutyl ether beta cyclodextrin, and the branched cyclodextrins such as glycosyl beta cyclodextrin. The most intriguing properties of cyclodextrins is their molecules that are able to form solid inclusion complexes and are known as host gas complexes with a wide range of solid, liquid, and gaseous compounds by following a molecular complexation protocol. What is a molecular complexation protocol is? whenever a gas molecule is making an inclusion complexes which is sterically favorable and thermodynamically favorable. So the most widely known pharmaceutical application of cyclodextrins is their ability to enhance the stability, solubility, bioavailability and safety of the drug molecules. These characteristic properties of cyclodextrins or their derivatives make them appropriate for applications in analytical chemistry, pharmaceutical chemistry, agriculture, in the development of food flavors and the toilet articles.